In this lecture, we will calculate the first order correction in wave function or state vector. In the last lecture, we have calculated the first order correction in energy, right? So in this lecture, we will calculate the first order correction in wave function. So for that, we will expand the first order correction in the state vector in terms of the already solved states, right, which are undisturbed. So what we are doing, we are expanding. So we expand these first order corrections in terms of phi n, right? So these are already solved states. We know the solution, these solutions. So how do we expand the vectors in quantum mechanics? So I will just give you one example from the geometrical vector expansion. So geometrical vector, if it is in Cartesian coordinate, you can write it as x1 x1 cap plus x2 x2 cap and x3 cap, where this x1 is x coordinate, this x2 is the y coordinate, this x3 is the z coordinate, and these are the unit vector along these three axes x, y, and z. So what you can do is that you can write it as summation xi cap, where I is 1, 2, and 3. So this is what you can do, right? And where this xi is the ith component of this particular vector, so it may be x1, x2, and x3. So if you just want to calculate the x1 just x1 component, so what you can do, you can take the dot product uh, of this particular vector r with the unit vector in that particular direction. So for example, how you can calculate x1, so you can take dot product of the vector with x1 I cap, sorry, x1 cap, which will give you x1 cap plus x2 cap plus x3 cap dot x1 cap, and this x1, when you will take dot product with this, these two terms will be 0 and they will be just x1. So this way you can write, you can just calculate the component of vector by taking the dot product of that vector with the unit vector along that particular direction. This is what we will replace this particular component by the dot product with the vector of that unit vector in that particular direction. So this is a way to write the expansion of the geometrical vector in terms of unit vector xi. So similarly, we can write the expansion of this particular vector psi n1. So we can write summation, we can take dot product of this particular vector with the basis in which we are expanding. So we will take the dot product of this particular vector with the basis that we are expanding in. So it is just phi m, right? So we have changed these indices. I'll explain you why we are changing these indices, and this summation is just for m is not equal to n. So this is how we can expand the state vector psi n1 by using this geometrical analogy, right? So just to calculate this particular quantity, we need to calculate this particular product, because we already know these states, these are solved states, unpart of states. So if you just want to calculate this particular first order correction, so you need to calculate just this particular quantity. So how you will calculate this particular quantity? So this particular quantity you will calculate from equation B. In the last lecture we have seen what the equation B is. We have derived this particular equation, which is very important, right? So what we will do, there the quantity that we want, so we will multiply this particular equation by a bra of phi m. So let me write it here. It is h naught acting on psi 1 plus W acting on phi n E n naught into psi n1 plus E n1 into phi n. So now just multiply this equation by this particular vector, right? So what will happen? It will be phi m h naught psi n1 plus phi m w phi n is equal to, this particular quantity is scalar, so it will be out of the product. I have explained you in the last lecture. So it is just basic multiplication, and this will be the result, right? Now again, I have explained you in the last lecture that if you act this particular Hamiltonian on the already known solutions, so we know that it will give us the uh, already known energies and the state itself. Because we don't know what the W is, so we will not do anything with this term. So just write it as it is. And we want this particular quantity, so we are not doing anything to this quantity as well. But we know that these states are orthogonal, right? We have assumed already that these states are orthogonal. And if these states are orthogonal, then if these indices are different, then their dot product has to be 0. So this particular term is 0, just we are leaving that term as it is. Now we are just here to calculate this particular term, so you can rearrange them and it will be phi m psi n1, and you can just take this term on that side, so it will be E n naught minus E m naught, which will be equal to this particular quantity phi m w phi n. Now then this term will be, by doing basic algebra, it is phi m w acting on phi n divided by E n naught minus E m naught, and we have calculated this particular quantity. Now just put this particular quantity at this place and you will get the first order correction in wave function. So let me assume this equation as f. So putting equation f in equation E will give us phi n1 is equal to summation for n is not equal to m, so just it will be phi mw phi n over E n naught minus E m naught into phi m. So this is the first order correction in the wave function. This is the quantity that we were looking for. So it is very important quantity, right? Now if you just want to write the energy and eigen function or eigenstate up to the first order correction, then you can write it as, so the energy of the state was assumed to be in the power series of lambda, so up to first order it will be like this. And in the last lecture we have calculated the value of this particular quantity, and by doing just it was phi n w phi n, because lambda is the scalar quantity, so it can be taken inside the product, and the energy of the system up to first order will be phi n, and when lambda will multiply with this w, lambda into w is hp. In the first lecture we have assumed it. So this is the energy of the system up to first order correction, and similarly the wave function of the system up to first order correction. So the wave function was like that up to first order correction, so it is just as it is. it is lambda times this particular quantity that we have calculated, first order correction. So it is summation phi m w phi n en naught em naught, and it is phi m. So just multiply this lambda inside, and it will be lambda phi, sorry, summation phi m. It will be hp because lambda into w will be hp, and phi n en naught minus em naught, where n and m are two different states which we have solved already, so we know what these quantities are, and this is the corrected wave function up to first order, right? So these are the very important equations. So let me say it h and let me say it I. These are the corrections, the first order correction in energy, right? So this is the first order correction in energy, and this is the energy corrected up to first order. This is the correction in the first, sorry, this is the first order correction in wave function or state vector, and this is the corrected wave function of the disturbed system up to first order. So in the next lecture, I will show you the calculation for the second order uh, correction in the energy, and that will be the end of the time independent perturbation theory for non-degenerate case. After that, we will study the degenerate perturbation theory, which will be little more tricky. So thank you for this lecture.